This video covers a variety of different ways we can think about covering nodes or edges in a network. Effectively, what we're going to be doing is building subgraphs of a network such that they have certain different types of properties. So we can talk about trails and circuits where we don't repeat any edges. We can talk about paths and cycles where we don't repeat nodes. We can talk about tree subgraphs within a network such that we only keep edges such that there's only a single path between all node pairs. And then we can talk about something called a matching, which is effectively finding edges that don't touch the same nodes, so vertex disjoint edges. And because this material is not in the textbook, it's because it's slightly more graph theoretical. I'm going to talk about all of these topics in this video. Our first way of covering a graph, we'll talk about a method of finding edges, essentially trails or circuits, such that they visit edges, all of the edges of the graph, never more than once, but exactly once. In the case of a trail, it's a single sequence, essentially that they can start and end at a different point. In a Eulerian circuit, it's that you start and end at the same node. And so it's intuitive to think about the fact that if a Eulerian circuit needs to reach every edge, then that means that it needs to come into a node and also out of that node to continue along that circuit. And so for that reason, every node has to have an even degree for there to be an Eulerian circuit. If it's a trail, then we have to change that a little bit because the beginning nodes could possibly have an odd degree. Beginning and end nodes could have an odd degree. And so that's exactly what this is saying, is that either you have no nodes with odd degree or you have exactly two. So these are conditions, and so the next thing we're going to do is look at the algorithm to find Eulerian trails and circuits. So to find an Eulerian circuit, we will start at a vertex V, and you're going to select a trail that returns back to V, so you're trying to find a circuit. Remember that you're essentially using edges, but you can go through nodes as many times as you need to. And so since every node does have an even degree, you're guaranteed that you must be able to find at least something. And so if this is already a Eulerian circuit, then you can stop. You've already found it. Otherwise, so that means that all of the edges would have been visited. But if there are edges that are not visited, then what you do is select another vertex and identify another circuit that that comes back to that same node. So if that next node that you identify, W, what you're going to do is try to find another circuit starting and ending at W. And then you're going to add that, essentially insert that into the circuit that you had before. And so this is a type of cover that is easy to find. So this is just linear in the time of edges. To demonstrate this concept, or this algorithm, we'll run it on this simple example. So if we start at F, at this node F, that we essentially find a circuit from F back to F. So again, we're never reusing edges. We're visiting all edges once, but we can visit nodes as many times as we need to. So in this case, we could possibly find the circuit that starts at F, goes through C, D, and comes back to F. And so we've used up some edges, and so this is our current circuit. That clearly doesn't include all of the edges of the graph. So now what we do is we select another node, one of the ones that's currently in our circuit. And so if we select node D, or kind of arbitrarily, then we can start with D and we can find another circuit that starts and ends with D. And so we can find the circuit that goes D to A to B back to D. And so the idea is now that we're going to take this new circuit and we're going to insert it where we had D before. And so now you have FC, and then we introduce DABD, and then continue on to F. We still haven't used all of the edges in the graph, so now we're going to select another node that still has some edges that are unused. So we could select node A, and then we find another circuit that goes A to E to C back to A. And so now we've used all of the edges in the graph. So now, as if we insert this piece in where A was, effectively creating this new term, then we have now found an Eulerian circuit. And so this algorithm actually is used rather widely. You can imagine that if it's important to reach every edge in the graph, then the Eulerian circuit is the answer to that. And so one way that you can imagine that is the garbage trucks. They need to, in Dallas, they go through the alley system, but certainly have to visit all of those. And so it's important for them to find routes and efficient routes where they're not necessarily going back and forth along the same roads. And so this is an effective way of finding short paths, in the sense, these circuits that eventually cover the entire graph, but never are repeating edges along the way. The next notion that we'll introduce is the notion of a Hamiltonian cycle. And so now we've switched over to essentially a covering, in this case a sequence of nodes and edges, such that every node is included in the graph. So these are paths and cycles are ones that don't repeat nodes. And so that automatically implies that you can not only not include a node a second time, but you can also not include an edge a second time. And so this is an example of something that seems quite similar to what we just talked about, the Eulerian trails and circuits, but this is actually an extremely hard problem and in fact does not have a polynomial time solution. Just as a simple example, this graph here, we can find a Hamiltonian path. We can go A to B, B to E, E to D, to C, and back to A. So we have not used all of the edges, and that's fine. The only constraint is that we need to visit all of the nodes, and we just can't reuse nodes. This network, which is quite similar, is not possible. You can't actually do that. And one way of seeing that is that if we have to visit B, C, and D, then we have to use this edge to get in and out of B, this edge to get in and out of C, this edge to get in, these edges to get in and out of D. And so that means that this edge is going to be used, this edge is going to be used, and this edge is going to be used, which means that A is going to need to be used more than once in order for there to be a cycle that includes all the nodes. And so that means since we have to reuse A's, then that's a contradiction, and this is not a Hamiltonian. It's not possible to make a Hamiltonian cycle. The same logic also applies to visiting E. All three of these edges need to be used. So finding a Hamilton cycle is a tricky problem. It's a hard problem. We can use an example to demonstrate why this is, and then we can also understand just some simple necessary conditions that if the Hamilton cycle exists, that at least we must have these conditions. So for example, if we're talking about undirected graphs, then at least it needs to be connected, and then that generalizes to strongly connected if we're dealing with a directed graph. So you have to be able to reach all the nodes. Because it's a cycle, essentially you have to enter and leave every node, so the degree has to be greater than or equal to 2, and if the degree is equal to 2, then both of those edges are part of the Hamiltonian cycle, which is what we used in the previous slide. And then it's worth noting that we have n nodes in our graph, and the idea of the Hamiltonian cycle is the fact that it's a cycle that visits all of the nodes exactly once. Then that means that it's going to be a cycle that has length n. So we look at this simple example up here, and so if let's say we just kind of start with node 1 as kind of a beginning point, then we could explore all of the different ways that you could reach all of the other nodes, and and then get back to 1. So the ones I've underlined here in green, these are ones that have an edge back to 1. Notice that 4 has no way of getting back to 1. So if we end at 4, that's going to be a dead end. And so so essentially this tree that we're doing is expanding all of the different ways that we can leave from 1 and navigate through the graph. And so 1 can connect to any of its neighbors, 2, 3, 5. Each of those can connect to its neighbors, and then we just keep track of whether or not we've actually reached. We've already visited a node, so that you can't actually use that node or that edge to get back. And so it's this combinatorial, so there's a lot of depth in computational theory for algorithms, but the gist that you can get here is that this kind of combinatorial explosion, this tree that keeps branching and branching and branching, you can imagine if this was a bigger graph, this would get ungainly very quickly. And this is a hallmark characteristic of NP-hard problems. And these are ones for which there is not known ways of solving the problem, or there's no known algorithm that can solve it in polynomial time. So there's no big O of n cubed, n squared, log of n, so on. Even though finding a Hamiltonian cycle is a hard problem, it is actually a very important problem. And so it's often called the traveling salesman problem. The traveling salesman problem is that you have a set of cities that you'd like to visit, and the salesperson would like to make sure to visit all of these. They don't need to visit them more than once. But they need to make a cycle, and in particular, they don't want just any cycle. They'd like to have the cycle that minimizes some cost, and that's usually a function of the weights. So we could indicate this flight between these two cities as having either a cost, monetary cost, could be a distance, the amount of time it takes, could be fuel if you're actually doing this to route packages around the nation. So this is a very classic problem in optimization, and one for which there are many heuristic problems, but not exact algorithms. And so oftentimes this problem is used to benchmark new methodologies for building heuristic algorithms. Like I said, it could be found not only in kind of routing and logistics, but could even be the same thing that's used when you design a circuit board, and effectively you need to maybe, for example, drill different holes at different places for the circuit board, or actually draw the circuitry out, and you'd like to do that in the most efficient way possible so that you don't have to move the tooltip more than you need to. So this type of problem finds its way into many different applications.